Hello everyone, and welcome to our Tech Team webinar, Materials Considerations in Radiation Processing, Polypropylene. My name is Sarah Krell, and I'm a product manager with STERIS Applied Sterilization Technologies. I'll be the host for today's event. Betty Howard is the presenter for today's webinar. Betty is the Radiation Tech Team Manager for STERIS Applied Sterilization Technologies, managing technical support and validation activities for gamma sterilization. Betty has over 25 years experience in biotechnology research, applications, and technical support related to drug discovery, analytic instrumentation, microbiology, biochemistry, and sterilization technology. We'd like to encourage everyone to submit questions at any time during the webinar. Once the presentation is completed, Betty will answer the questions in the order they were received. You can submit your questions by typing them in the questions field on your GoToWebinar control panel. If you have a question that we don't answer in the time allotted, we will address it separately in an email following the webinar. Today's presentation will be recorded, and we will email a link to download the file to all participants. Please note that continuing education credits are not provided as part of this webinar. And now I'd like to turn the phone over to Betty to begin the presentation.
Okay. Hello, everyone, and welcome. Thank you for all attending on a very unique topic for me. Usually when I'm speaking to you, we're talking about the details of making a product microbiologically sterile and the probability that a selected dose will assure that that product sterility is met. But in reality, think about what you're really making when you're making a healthcare product. The process for setting a dose, once you pick a method, is quite defined and consistent product to product. But the real goal here is to have a product not only be sterile, but to still achieve all its required claims, predict its lifespan, all the while making sure it's a safe and effective product for use. To achieve this real goal, you start much earlier than setting a dose for sterility. You start with more with what will happen to the product when you treat it with a sterilant. So it's not just the act of hitting it with a sterilant or a sterilizing process. We have to consider very early in development how these things are going to match together, all of the things you're using to make the product, your processes, and then at the end when we come in and we do something to it to try to get that microbiological effect. By focusing on the material selection of how you make your product very early in development, many key problems that occur and that slow your progress down can be avoided. We're going to look at material selection today by focusing on the information available and what issues you should consider when using one particular polymer group, the polypropylene. Okay. Now, let's see. Oh, I have to make sure I have control. And okay. Ooh, I got a little ahead of myself. Sorry, people. Our overview for today's seminar is we're going to look at what polypropylene really is, what material considerations you need to be aware of when using it, some of its limitations, but also the really good point about dealing with polypropylene is we can look at things that can be used to assure your success with it and to correct known problems or known misconceptions about its use. Okay, let's start out with what polypropylene is. Polypropylene is a long-chain carbon molecule, hydrocarbon. Diagram is over onto your right. It's considered a thermoplastic. That means it's the kind of plastic that can be reprocessed. It has a well-defined area in which it usually melts, which is important for getting it into molds. And its density is pretty well documented. The properties of an individual resin will depend on the molecular weight, the degree of crystallinity, and the percentage of any additives, particularly copolymers, if they're present. When you're comparing the trait called crystallinity, which we'll talk about a little more as we go along, it's considered semi-crystalline, and its behavior will be in between the two best-known polyethylenes, low-density polyethylene and high-density polyethylene. Okay. It's commonly used for many healthcare products as well as labware applications. The reason why it's used is it's an excellent material. It has great mechanical properties, good thermal properties, it's relatively low cost, it's good for moldability, it's used frequently in injection molding, blow molding, and many other processes that people would try. It's considered safe. It has good known biocompatibility, so nobody using it automatically has to be concerned about the benefits or the possible damage to a living cell. It has excellent moisture resistance, so things are not going to seep into it if it's in a moist or humid environment. It has very good chemical resistance. The one exception that is more common would be that it doesn't do well around chlorinated cleaners such as bleach, and that fact that it can be reprocessed. So basically mistakes can be fixed, or at least the material can be reused for another purpose. Common examples of what it's used for, probably the number one place you see it is in syringes, but the parts that are more of interest to me and have a more likely chance to cause a problem are connectors and clamps and stuff on assemblies, but containers, lids, test tubes, laminated sheets, some of your package materials or covers. And as you start thinking about where you may use them or where you've seen them used, you'll find polypropylene in many, many different things. Okay, why did we select this material for today's topic? One, very popular. It is one of the few plastics that are used in healthcare products with known concerns when used for products that will be terminally sterilized with radiation processes. There's also extensive data available on its effects, and considerable amount of work has been done over the years on trying to define why those effects occur. So a lot of times you see a problem and you don't really know why it happened, but the information that's known about polypropylene has been continuously being added to and is readily available. It has, we also have a product with known problem potential, but also has known ways to reduce or eliminate some of those concerns if selections of formulations or additives or changes in how it's used are considered early in development. It's also popular to me personally and my group, the Radiation Tech Team, because by far it is probably the largest point where questions come in response to a failure. It is not uncommon to have somebody call and say, the product when it was irradiated is now leaking, or a connector cracked, or something has got crack lines or craze marks on it. And frequently the first question we will ask is there polypropylene in the product? And you would be surprised how often the answer is yes. Think about if you've created a product design that could be very complex, that was engineered specifically for a use. If one little tiny component like a connector fails, the whole design will fail. Okay. What actually happens when a polymer, not just polypropylene, but any polymer, is actually irradiated? Well, several things are possible. One is that it could continue to polymerize. For example, if there are free monomers, meaning the reaction was not completed, the radiation, the initiation with ionization will cause those chains to continue to form, so they will get longer. It will have the possibility of cross-linking, where things will start to create a network of bonds within the structure, increasing its crystallinity and increasing its density. Think of it as shrinking in as it's cross-linking in. Scission, which is also referred to as degradation, making smaller molecular weight fragments of the same thing. So where you had the long chain, now you've got the same material, but it's chopped up in little bits. Double bonds can be formed where they did not exist before, and these can create reflection of light as it's passed through there that can be very different than it was before the double bonds were formed. This reduces the elongation properties, how far you can stretch them out, but it also can create visible color changes that are frequent, if not functional problems, can be aesthetic problems. But they can be functional problems, particularly where light has to pass through an object. Yellow can shift the wavelength of a light that's passing through an object. In other cases, it can just make it look kind of funny. In general, polymers will tend to experience multiple reactions during the time they are being irradiated, but usually one dominates over another, and that's the major contributor to effect. You will see when you look at different polymer specifications, many times they will give you a number called the ratio between cross-linkage and scission, and it's a good way to compare them. The most important note here is that every one of these possible changes can impact physical properties. The other one is that all changes as a result of radiation are cumulative and are affected by the total dose. So whatever effect it is will continue to get worse as the dose increases. And they don't self-correct when the irradiation process stops. You have to consider the change to be permanent. Okay. For polypropylene specifically, it's actually a very phenomenal material when you start looking at it as a chemist or as a scientist, that something so simple can create so many different phenomena. Okay. What we see here is that with polypropylene specifically, cross-linkage will impact tensile strength, so how strong that thing is when you press against it, especially in the first 48 hours post-irradiation. That cross-linkage function will continue, but more slowly over time, even over months. This is important because if you looked only at the product the first hour or so after you got it back and didn't look at it a little while later, you might miss something that you might need to consider in terms of the life expectancy of the product. Copolymers of polypropylene will frequently be labeled as a copolymer on your specification sheets. What they really are a blend of polypropylene with other more radiation stable polymers, things that are known to have a tendency to cross-link. In general, a product that cross-links will be more stable to radiation than one that predominantly will go through scission, because there's a limit to how much cross-linkage it can do. So if you blend in polypropylene with something more resistant than it is, for example, frequently the additive would be polyethylenes, those types of materials together will be better than either one separately. The addition of the more stabilizing plastic will increase the tolerance of the polypropylene, correcting many of the known problems that will occur with it. In the presence of oxygen, though, polypropylene will also create scission events, creating, as a result of the free radicals it created during the irradiation process, that will yield chain breakage. This will tend to cut specifically at that tertiary carbon present in every one of those repeat segments on that structure. As an example, it's important to know that all these changes can be dramatic at doses much lower than you're probably thinking you're going to need for a sterilization process. For example, the first thing most people think about when they're talking about a radiation stable product, they're thinking, oh, I can run this 25 to 40 or 50 kilogray. In the case of a natural polypropylene, the simplest polypropylene you can find, if you work with that material, it will never be able to tolerate the types of doses you need to get a 10 to the minus 6 sterility assurance level. These pictures here are just a quick, easy example. We all are pretty familiar with what this object is, and we know what it looks like. Looking at the picture on the left, there's two containers. One, depending on how well your resolution is, the one on the right is very clear. It looks like your standard polypropylene cup. The one on the left is much more yellow. The reason why that's important is not just the coloration. The coloration is a tip-off of what's going to happen. The picture on the right is me taking that one on the left and just whacking it slightly. It will crumble in your hand if you try to hold it, if you apply any pressure to it. Even at lower doses, it will at least make craze marks on it that will be points of weakness and will increase the likelihood of additional scission events in the presence of oxygen. So the changes can be dramatic. So you always want to keep track of when you're seeing a color change, know it's there, know that it's not necessarily the main issue. There may be an underlying issue that's coming up behind it. Okay, the visible effect is that discoloration. This is frequently a precursor to significant mechanical changes. Color alone does not mean embrittlement in a polymer. Double bonds formed and the addition of phenolic type antioxidants are frequently related to yellowing. Those additives may be the thing that's yellowing, not necessarily something physically changing with the plastic. But remember, they're in there, and they will always be in there. So you're going to see the color, but while that's happening, know that at the same time, you're going to have these other events going on that will cause mechanical changes. For those of you who mold things, the melt viscosity will be significantly changed when it's irradiated. Up to 2 orders of magnitude have been observed. So there can be changes in how it will fill into a mold. Okay. Additives. Additives to polymers, usually we think everything should be pure. In the case of a good plastic, you don't want it pure. You want it to be engineered for use. Additives to a polymer are there to allow it to tolerate the heating process when you melt it to mold it, to affect the flow rate into your mold. They have free radical and antioxidant scavengers in there to take away a lot of those ionizations that could cause other damage. There are things in there to make them seize up and settle and harden to make your plastic properties. And these agents are there for good reasons. They are helping influence those mechanical properties long-term on your product. They are significant. They can be as high as 30% of the total weight of that polymer. Key importance is they are needed. No polymer is used in its pure base form. The stabilizers that they may add, some stabilizers that are added, a few of them, are not usually enough alone to avoid embrittlement, but they can cause color. Copolymer blends usually will reduce embrittlement. They're more likely a blend of a other polymer that has in its structure most likely aromatic rings, what you probably the benzene ring. Benzene rings are considered very stabilizing to a material that will be irradiated. So blending in things like a polyethylene or a polyethylene or a polymer with some additional elastomeric properties, these things provide those structures that can act as a sink for a lot of those ionized particles so that they don't mess with your structure as much as they would if they were free to continue down all of the material in your system. It is always a recipe, and the final recipe is what's important. Ingredients take into account the purpose and manufacture of a product and how it will be used. And think of a recipe just like you would food. Grandma's spaghetti sauce and the spaghetti sauce in a jar. Both of them are spaghetti sauce, but one or the other you'll probably like better, and it will fulfill your purpose better each time. Okay. One of the ways you classify a polypropylene, when you get a resin for manufacture, you always get a specification sheet on it. Its description at the very top the first thing it will usually say is either natural polypropylene or homopolymer of polypropylene. It'll say a random copolymer. Sometimes it'll use a variation on a random copolymer called a heterophasic copolymer, which is just another form of one. But the reason that is important is that tells you right away whether or not you should be highly concerned about the stability and radiation. Each version adds different properties to it. Some of the key properties you look for on a polypropylene are how rigid it will be, how much abuse it can take, like opening and closing a cap. Transparency, how clear it's going to be when you look through it. Can you see through it or not? A homopolymer, the best of the formats, if it's the homopolymer, it's going to be the best of the 3 types in rigidity. It's going to be the worst in terms of abuse. It's kind of in between in terms of being able to see through it. It's going to have that little bit of cloud to it, but you'll be able to see things through it. A random copolymer, a little bit less on the rigidity. It's really good on the abuse profile and really bad in terms of transparency. So it'll be more opaque looking. A heterophasic copolymer is still a copolymer. It'll usually have dispersed into it a elastomeric rubberized type of material that gives it additional properties. So it's not great on rigidity because it's got that elastomer in it. It's kind of in between on the abuse, but it's really good in transparency. So by adding additional types of things into that base homopolymer of polypropylene, you get some additional properties that can be actually quite rewarding. Okay. So as a rule, homopolymers will be less stable than any form of a random copolymer. So when you first see homopolymer, doesn't necessarily mean it's always bad, but it means you should probably ask some more questions. A dose as low as 25 kilogray can decrease the impact strength on a homopolymer of polypropylene by 50%. Not a hard and fast rule because that will depend on the specific resin, but you always want to ask questions once you start seeing the words homopolymer on a product. Okay. This is just to give you the fact that there is data out there. And I've got at the end of this, I've got references. So any of the data I have comes from actual experiments that were done and published. The curves on the top, the red and the yellow one, those represent random copolymers and how rapidly they will drop in terms of their elongation strength and break, and how they'll be consistent. On the homopolymers, they drop rapidly and go down to next to nothing. So they lose a lot of their mechanical properties much more quickly than the random copolymer will. Okay. Discoloration. The most common cause of discoloration is a phenolic stabilizer. It's added to improve the resistance to irradiation, but it will discolor. The other effect you're seeing is anything that happens in terms of double bond formation, which is a byproduct of some cross-linkage. It's going to deflect the light passing through it very differently and shift it to the yellow. Color in a polymer, even polypropylene, does not always mean embrittlement, but is a warning. It also may not be reversible, so you have to either accept it as is, as long as the other mechanical properties don't change, or make changes to the polymer to avoid as much discoloration as possible. Theories on degradation. We know it breaks. I can demonstrate it over and over again, and any of you who have been to some of my seminars have seen me do this. It is not lightly brittle that happens when you sterilize a homopolymer of polypropylene. It will be dramatic. It will explode in your hand by just slight pressure. Think about a healthcare product that a patient is using, whether it be a specimen cup, a syringe. You've got to accept that people are going to put impact on it, and you don't want it to break. One of the biggest theories on degradation is by looking at the oxygen diffusion rate into the product. And this actually accounts for one very well-known phenomenon, that thin films versus big, bulky products actually experience more rapid decline. And that's because the oxygen can permeate through them readily and much more quickly, so the change can occur. Another thing we've learned is that dose rate can affect oxygen permeability. So if you think about the longer it takes to deliver your dose, that's a longer period of time when the conditions for a change to occur are there. You have oxygen present and you have an ionizing field. So dose rate can impact the available oxygen in the product. And as an article at the end, the reference is the particular authors that has a whole bunch of data where they've demonstrated that permeability. So I wanted to actually show you that because I think this is a phenomenal slide. If you think about a product when it's made, it has some residual oxygen in it, in its matrix. Once you ionize it, that internal oxygen is very quickly depleted. It can be replaced, though, by oxygen on the outer surfaces, but it has to be able to have time to permeate back into the product. As more oxygen permeates in, still with ionization going on, more and more change can happen. as a result, it is possible to see some of the changes in a product when they are oxygen driven be different in total amounts of change when you look at a very rapid dose rate, for example, that an E-beam unit can produce versus what a gamma unit can produce. And this picture shows where you've got a deeper penetration of the oxygen on the product when it's gammaed versus the one that's E-beamed for the same dose. And that's because the electron beam is depositing in a very narrow, discrete path a lot of ionization events very, very quickly, and then it's turned off. So one of the key features to have that change occur, which is that the oxygen and the ionization be going on at the same time, is stopped. Okay. So what can be done to successfully use polypropylene? The key is always planning. Remember that all resins are not the same. Not all polypropylene is bad or good. Each specific resin that you buy, by part number, not even just by company who makes it, is different. It was engineered for a specific function, and included in that function is how it will be sterilized. Okay. The next bunch of slides are going to be a lot of things that I think key considerations you want to take into account when you're picking your plastic. First off, work with the resin supplier. Don't tell him you want polypropylene. Tell him you want polypropylene specifically, what you're going to make out of it and how you're going to sterilize it. Because they can guide you toward parts or products that they make that are engineered for that use. If you need something special to handle particular conditions, many times they can engineer these or point you in the direction of a specialty formulation that they already have. There are frequently many versions of the exact same base polymer. So the other thing I would recommend is that you always evaluate more than one resin in development for a really good reason. Sometimes you find something surprisingly good when you do that, and the one you thought you were going to use, you won't. But the other event that can happen more often than not is Murphy's Law takes effect, and the bad thing happens when you least expect it. You could be working with a material you've worked with for a very long time, and then with other products, and find that for this new product, it creates many, many problems. If you haven't been looking at more than one resin as you've progressed through development, you are now starting over with a new material, and you've lost all that time. This is an example of a snapshot out of a provider of polypropylene. This I always use an example to prove to you that there is not just one part number called polypropylene. This whole list represents many part numbers that are called polypropylene. The beauty of this kind of information, and it's information you can always get from a resin provider, it'll have the part number, it'll tell you immediately whether it's a homopolymer, they may call it a natural polypropylene, they'll tell you if it's a random copolymer, and they'll tell you if there's something exceptionally special about it. They will also give you mechanical data on it, on things that they can test, that maybe, but remember they're testing a material, they're not testing a product. And they'll also tell you what it was engineered for, whether it was engineered for blow molding, whether it was made for a product to be terminally sterilized in irradiation. This can give you a chance to avoid selecting a resin that really is not ideal for your purpose, where another one line down, could be perfect. It's always best to know what it was made for, so that you're picking one that you have a chance of success with. Okay. The other one is, do not be afraid to ask questions. If you see that a part number of interest is a homopolymer, ask them if it's considered radiation resistant. Sometimes it will be labeled gamma stable. Ask that if it's not listed on the spec sheet. Is it a copolymer? If so, does it have the properties I need? That's when you start looking at those mechanical properties and the functional uses of that resin from the specification sheet. No resin supplier will promise you a dose range of tolerance. They will not say, sure, you can make your product out of this polymer and sterilize it 25 to 50 kilograms, you will have no problem. It's not that they don't want to, they can't. Any polymer's result is affected by not just the resin's name, but how it's processed, the design that it's being formed into, how it's used, how it's going to be cleaned or terminally packaged and processed. All of the steps up until it gets to one of my guys and they actually sterilize it. Every one of the steps it experiences in manufacture can impact that final performance of a polymer. And that is critical, and we're going to get into that in a little more detail too as we go along. But always ask questions. There's never a bad question, and the more you know up front, because you know more about what you're asking the polymer to do than any supplier or any sterilizer will. You want to make sure you evaluate the sources of information you read. I cannot stress this one enough. I frequently get people who will call me and say they have irradiated an object 10 times, but that the material can tolerate 10,000 kilograms, so they want to know why I destroyed their product. Just because a polymer in an engineering data table says it can tolerate a given amount of kilograms of dose does not mean your product can tolerate the same doses. Frequently, when these tables are made, they are looking at one characteristic of change, most notably the change in elongation. And they consider good, an engineer considers good, an elongation change of less than 25%. Not too many products in healthcare can tolerate a change in tolerance on the elongation, which will affect the rigidity and impact strength, of 25%. So you have to judge these with a grain of salt. They also are frequently evaluating test samples or dog bones or tensile bars. They're not evaluating a product with bends and curves and stresses on both sides of a bend. All of those things impact the effect of oxygen permeability, cross-linkage potential, and the added stress drives more oxidation. So you have to always know that the tables are great as a starting point. They are not a replacement for testing. They do not reflect the exact resin you will use either. They are generalized tables unless you're getting them from the resin supplier. Color. Most of the time, the first thing you'll notice with something that's been irradiated in general, but polypropylene exceptionally, is that it will turn yellow. Most of the time, not an appealing yellow, something that makes it look old or dingy. But there are ways to look at color. Color can be masked to get rid of the yellow. One of the most common things is sort of like if you can't beat it, join it, which is put something in there that's opaque and just snows out the yellow. That's why you see a lot of times colored caps, blue, orange, bright colors that are so intense they block out what you see as yellow. The other key solution that is frequently used is the addition of blues to the actual resin. So when you have that clear-ish resin where you want to be able to see through it, frequently blues will counteract the impact of yellow. And that's because of the wavelengths of light. They will cancel each other out. What looks yellow with the addition of blue, once it's processed, will probably look clear. When you make the product, it will have a slight blue tint. But when it's irradiated, the blue goes away as well as the yellow. So it's actually a very nifty thing to see. Okay. Modifications to resin designs. That's where your additives come into effect. You can do things in your specifications, the formulas, but remember, many times, I would say most of you are probably not resin chemists or polymer chemists. If you are, congratulations, your day has come. Everybody is looking for a really good polymer chemist because they want to increase the properties of the common safe plastics that are used in healthcare. But let's look at what you can do when you're adding things to a formula or making modifications to it. Think about the molecular weight of a long chain polymer. How long that chain is impacts the molecular weight. You could have in a bottle of resin a wide variety of molecular weights of chains. The more narrow that distribution is, you'll limit the variability of your response. So when you get to a resin that's really, really good, those properties, the effects will be very pure and very discrete. If there's variability, you may have more effect on the ones that are shorter versus the ones that are longer, so you can get some very different things going on all at the same time. Sometimes there's additions of hydrocarbon oils, and they're frequently added as plasticizers. They too become a sink for a lot of this ionization activity. Additives in general will reduce crystallinity. They will keep the product from making these three-dimensional mesh structures in there, which can help control embrittlement. The amounts, the choice, the general mix, the overall recipe of all of these things that can be added will vary. And their choices are made based on the requirements of the product and its use. Another good one is particularly the stabilizer, the most common stabilizer being the phenolics, which we already know make yellow. There are some that are called hindered amine light stabilizers. Those generally cause less yellowing than the phenolics. So sometimes it can be as simple as getting a homopolymer that isn't stabilized with a phenolic, but stabilized with another additive that doesn't go yellow when it's irradiated. That's why you will see, even though I tell you to look particularly carefully when anything says homopolymer, you will be able to find things labeled homopolymer that are also considered gamma stable. And that's because they're taking into account some of this yellowing. Chemistry changes can improve the response. That's why all of this mixture goes on and why it's always being worked on. You will see more and more different formulations of any polymer, but dramatically wide varieties in the polypropylenes to account for all these mixes that can be made to try to engineer better and better properties. I want to make sure that. Oh, and the other one that can be a selective thing that I forgot to list on here is how isotaxic the structure is. You know how you had that structure, that long chain carbon of what a polypropylene is, and it has those little CH3 groups on them? Those are the bigger groups rather than just a hydrogen on the other end. The more of those that are off to one side, you make it harder for the thing to create three-dimensional structures, so it's going to be less likely to go into a crystalline mode. So it can actually contribute to the stability of the molecule. And the most important thing that you'll ever do with any product is test it. Test it. Evaluate the actual product design. Not one made something like it by a competitor, not made on an early prototype that you have no intention of making. One that's not with the material alone, but the finished product, including all the processing steps, molding, washing, any abuse, bends, folds. Always remember that strain drives failure. If you think of a piece of plastic, when it's laying straight out, the only stress on it is gravity. If you take it now, in order to form your product, you make a curve out of it, say a C, because one, it looks cool, but two, it also supports the function better. That one press down to make it a curve creates many different events on the same piece of plastic. On the top surface of it, you have elongation stress. It's being pulled. At the same time, on the underside of it, it's got compression stress. So you have it pushing on one end and pulling on the other. This is a condition that add to it. You have cross-linkage and oxidation going on. All of those together, you're adding additional reasons why the piece could fail. Think about a connector that looks just fine. Maybe you even put extra whitening in it and stuff like that so that when you radiate it, you don't even see it as yellow. If it was to compress just a bit more than your tubing set, for example, could hold it in place, you will get leaks. If you have a syringe and somebody was to press down on that syringe barrel, either holding the barrel and you could crack the barrel, but you could also break the plunger from the pressure pushed down. So looking at the strains of how the product will be used are critical. Repeating it, doing it the way somebody in use will use it, so you can see if that polymer mix will work for you. Okay. Product-specific claims are part of your specifications. Make sure that the product post-irradiation at the worst case dose you will give it, not nominal. Don't test them at 25 to 40 if you're going to run 25 to 40. Test them at 40 because you want to know that there will be no chance or very limited chance of a product failure due to irradiation at that higher end, because you don't always get the exact number of kilograms each time you process, and you certainly don't to every individual unit in a box. Thoroughly challenge them. Look at them spectroscopically. Look at the analytic things. Look at the macroscopic things. But consider always the impact on aging. Because these processes, the effects of the irradiation do not necessarily stop. The product will not be radioactive. But think about it. If you create a structure that gets more and more compressed and more crystalline, and in that matrix it has trapped ions, those ions at some point are going to continue to do something until they can come to rest and finish their process. So if you look only at the very short term, you may be missing something that will impact your lifespan on the product. That's also why aging studies, which are required anyway for any product that are labeled with an expiry date, will be particularly important with this type of polymer. You want to make sure you've got good data to support your projected lifespan versus its function. Okay? Design considerations. Many times we come up with these great graphics on how we think this product should be made, but keep in mind, each curve and each bend you put in a product could contribute stress. Thick to thick versus thin sections, or worse, transitions, like a thick piece going into a thin piece, can create areas where unusual events can occur. Complex curvy designs versus more simpler ones can have an impact on that internal stress on the product. Homopolymers versus random copolymers, that's going to be part of your choice on how far you can go with these curvatures. Evaluate more than one resin. Avoid the possibility of time being lost. Frequently, you have very tight schedules for getting either a modification of a product or a brand new product on the market. The more information you have up front while you're trying to create these designs is important. It will save you time in the long run. And you'll probably come up with something that is going to be more stable long term, because you will learn things about how the design is impacted by the polymer. Assume product cannot be re-sterilized. That is one of the great limitations with polypropylene, but in healthcare that's pretty much okay. Most products are not reprocessed. They're more often than not single use. And this is because the effects of dose are considered cumulative. This is a general rule. But since polypropylenes already have some inborn limitations, trying to reprocess them at another sterilization dose is in most cases going to result in failure, even with the use of a random copolymer, because you're adding to whatever has already happened. There's limited places where reprocessing becomes a norm. For example, having to replace a pack insert where the product is fine, but you've had, through some regulatory change, had to change the instructions for use. If you have to do that to a polypropylene object, you may not have much available dose left to be able to process it without damage. And if you don't have data on an extreme worst case dose that includes now twice what your original dose was, you don't have the data to support the dose range as being valid. Okay. The references I'm going to give you are things that are frequently, are easily available, for one thing. They give you actual data to show what's happening when these events occur. And they're in many cases are things that are recognized as part of standards, publications, or just overall sources for a lot of the tables you see on materials response. The first one on top here is the AMI standard for materials compatibility and sterilization. This one is near and dear to my heart because I'm actually on the AMI committee that's reworking this one right now. But the beauty of this document is that it includes materials compatibility information for not just irradiated product, but also for things of other common sterilants, including EO, heat, ozone. So it can be a good way for you to look across all of the possibilities and see which materials are particularly good or bad with that process. Overall, I will also in summary tell you that most polymers work very well in irradiation, whether that be X-ray, E-beam, or gamma. The ones that work well are engineered to tolerate those processes. But there are exceptions, and homopolymers of polypropylene are one of the most common exceptions in irradiation processes. The second article here is the one that has the information on that oxygen permeability. The next one is, you can actually find it online. It's from a conference, but the gentleman also wrote an article, and it goes through a lot of studies on homopolymer effects versus random copolymer effects. The next one is, you'll see many large documents over the years that were produced by NASA. And notice this one is actually quite old. The reason why that's really good information is think about why NASA wanted to know that. They were sending things up into space, so you have cosmic radiation for the entire time that that spaceship is up there. So there is an effect that's cumulative on products. So they really wanted to know a lot about materials. They looked at not just materials for making objects, but they also looked at things like the insulation on wires and cables that were going to be in the space program. The next two, Carl Hemrich's article and Barry Ferran's book, are excellent general articles on materials compatibility, the effects of a radiation process. So they're good overall views of trying to see what happens with polymers. And the last one also resulted in from a lot of the facts and figures in this presentation came out of that magazine. And that one was actually much more modern than some of the older things you'll see. But keep in mind, the laws of physics and the laws of chemistry frequently don't change. They stay the same. So these older articles where somebody did very discrete tests, the principles will still hold up. The difference will be that modern polymers are much better engineered than very old ones. So your choices on what you can work with are leaps and bounds better than they were in the 60s and the 70s. Okay, in conclusion, polypropylene is an excellent material used in all forms of medical devices. It's also very popular in labware. And one of the reasons why it's popular in labware is that frequently labware like test tubes and petri dishes and stuff like that are not used in applications that require an exceptionally high sterility assurance level, like an implantable healthcare device. Implantable devices require a 10 to the minus 6 sterility assurance level. Frequently, you will find that labware will have a 10 to the minus 3 sterility assurance level. What that means to you is that the dose required to sterilize it and be able to call it sterile is much lower if the sterility assurance level can be lower. And that's why if your dose is lower, many of the negative effects you would see in a polypropylene go away because it's driven by the dose. Polypropylene has many formats and modifications that are possible to select so that you get the best fit for your product's needs. It can be engineered, in many cases, to improve them, even to make them very specialized for your function. At any time it is used for a product that will be terminally sterilized with irradiation, it should be fully assessed. At times it may not be the best choice. There will be alternatives for polymers that may work just as well for your application. Most of the time, that probably will not be needed. It may be that you're comfortable working with polypropylene, you have a lot of experience with it, It's, you have a formulation of it that works well for most of your products, so by all means, work with it. But there will be products, there will be times where that may not be the case. But the good news is there are always new and improved resins being designed. We may not be creating brand new base polymers, but the world is creating many, many different formulations of those and mixtures of them. Some of them are not just two materials added together. There may be 3 or more things added into their polymers so that you get the characteristics of the summation, not just the one product. Okay? There's a lot of information here. There's also a lot of things that you guys may run across when you're looking at a particular resin. By all means, if we can help or we can direct you to additional information, feel free to contact me. My direct number is here, as well as my email address. Okay. And just so you know that the things that I usually talk to you about are not that far from my heart, we do have upcoming educational seminars that will be done in the area more directed toward the sterilization function and the setting of dose. And the next one, there is a webinar that I'm doing for Amy on the 25th, and our overall corporate seminar that we do across the country on the fundamentals of medical device sterilization using many modalities. I actually do a seminar on dose setting, gamma radiation, as well as materials compatibility on that. By all means, you can, I also should add that that seminar in Orlando, the registration ends next Friday. So if you do want to go to Florida in the winter, it's always a nice place to go. Okay. I am going to end on that particular point. I think you've got a good set of things to consider with polypropylene, and go from there when you're making your decision. Don't use this as something to scare you or push you one direction or other, but be an educated selector of a material. Your selection of material will probably be the most important thing you do in designing a product. And it's not always going to be one choice. It's amazing what you'll find out there that you can work with. Okay, I'm going to leave this open to questions. And like I said, if, as Sarah said, if we can't answer them all today, feel free to email me, or any we miss, we will email you back. And
right, Betty, we have just a couple questions, and first I just want to clarify too. Registration for the seminar actually ends this Friday, not next Friday, so just a few days left. If you go to the website isomedics.com and go to news and events, you can find the registration link right there. So just a few more days to be able to join us, like Betty said, in the warm Florida weather. First question, it was more of a housekeeping one, but I want to answer this one directly, and it was, can we share a copy of the presentation? We don't share the slides from the webinar, but we will be following up within the next day with a link to download the recorded version of the webinar, and we'll also place it on YouTube, so that way people will be able to get it either by downloading it or viewing it from YouTube. So we'll be excited to share that with everyone. Betty, the next question for you is, can polypropylene be modified through radiation to add valuable properties?
Yeah, actually it frequently is, because one of the things that does happen to it is it will, as it's irradiated, it increases tensile strength. But when it increases tensile strength beyond a certain point, it will also lose impact resistance. So depending on what property you really need, it can be engineered to make it better for what you need.
Okay. Next question is, do products need to be reevaluated if switching radiation source, such as gamma to E-beam or vice versa?
Okay, that's actually a really good question. When you're going E-beam to E-beam, the actual source could be different in millivolts, so you would evaluate them for that. If you are changing from gamma to E-beam, in general, the oxidative properties will not get worse. They should improve because of the shorter impact. But the conditions can be different. What I usually tell people to do is, if they're switching in either direction, E-beam to gamma or gamma to E-beam, that they at least evaluate the effect at the worst case to assure that there isn't something specific to the method that is giving you a surprise. It could be that the actual temperature achieved in processing could be different. It could be that the effect of the longer dose delivery in gamma is giving you more of an issue. It could be the fact that the gamma has time for dissipation of any internal heat buildup, maybe improves your process. But there are enough differences between them that it is a good way to at least check it. Maybe you don't do as full an investigation as you did when you originally selected the material for irradiation, but it's always best to at least gut check any change you make that's dramatic and that affects your sterility and lifespan of your product.
Great. Next question. Should shipping be delayed after 48 hours after irradiation of polypropylene to help reduce product breakage?
It won't prevent the breakage. And if you think about it, from the time we actually irradiate it to when you get it back, it probably has experienced more than 48 hours. But what can happen, what you're seeing is that's the first wave, most of the damage you would see. You're probably going to see it on delivery. So I don't think necessarily that's going to help you if you wait 48 hours to ship, because it's something you'll probably know what the impact is long before you're ready to ship product.
All right, and next and final question related to the one you just answered a minute ago is, we have a customer that intends to transfer their sterilization from gamma to E-beam and have noted yellowing of tubing using E-beam. I've always thought the dose rate in E-beam was more beneficial to reduce the negative effects. Any ideas why this might be happening?
Okay, it's still polypropylene. It's still got stabilizers in it that react to ionizing radiation. In general, you will see usually a difference in the tube, but it's not always a dramatic difference, especially if the polymer used was stabilized for radiation. It could be you're seeing an effect due to the localized heating, maybe because of the rapid addition of the dose. Maybe it behaves slightly different. Remember, too, that color changes are subjective. It could be when you switch to E-beam, it's better, but it's still yellow because the chemistry is still happening. So it doesn't make all of those things go away. It's just one of the possible tools you can use to try to alleviate some of it. I'll also add that in either radiation source, many times color will tend to fade over time. It rarely will go back to zero, but remember, it's still in an oxygenated environment and it's stored, it's exposed to light. So sometimes those double bonds that create the yellowing will reduce. You see it more dramatically on things like glass, where heat exposure or something like that will reduce the color.
Great. Well, that was the last question, and it leads us to perfect timing, as it's 3 o'clock about right now. So thank you all for joining our webinar today. We really appreciate you taking the time to learn with us, and we hope you found this beneficial. If you have any further questions, please contact the Radiation Tech team or Buddy at the information that she provided, or visit the Tech Team Resources section of our website. Thanks again for joining us today. This concludes today's webinar.